Module 2. Creativity and Innovation for Footwear Industry. Unit 2. Product-related Innovation. This unit contains the following lessons. Lesson 2.1. Innovative Materials for Footwear. Lesson 2.2. Engaging Digital Engineering Tools for Innovative Footwear. Lesson 2.1. Innovative Materials for Footwear. This presentation is structured on the following topics: innovative leather, alternatives to traditional leather technologies, smart and multifunctional materials, nanomaterials, biodegradable leather, biomimetic textile materials, shape memory materials, materials with thermal electrical properties, waterproof and/or breathable materials. The innovative leather has high functionality and environmental performance. Here there are several examples: leather tanned with trivalent chromium minimizing environment risks, lighter and more elastic leather for comfort footwear. Leather with good thermal performances and resistance to water, leather with greater resistance to light, leather with antibacterial and antifungal properties. Apart from the process of leather tanning, developments in leather finishing bring significant challenges to designers, too. Several types of finishing effects are presented below. Stamped, pressed and punched leather, printed leather, leather with strong silver accents, manually painted leather and handwriting on leather, leather with irregular metallic effects. When fashionable special effects complete the environmental responsiveness, the result is enriched. For example, the all-Jimmy concept was applied in collaboration with German brand Trippen to create a collection of the microalgae printed shoe. A natural pigment that has the property of changing its color in various sun or light ambience was used. One example of successful research in innovative leather is NanoFoot. The project developed advanced and innovative nanotechnology-based solutions for leather and polymers components for footwear. NanoFoot project investigated new antibacterial and antifungal leather based on nanoparticles nanofillers with enhanced comfort features such as high breathability, thermal and electrical properties, water resistance. Looking for alternatives, the innovation in leather processing could include the following topics: leather obtained from various animal organs. For example, the Dutch designer Mandy Denelsen created a leather-looking material, rumen leather, with a hexagonal structure using the cow's stomach. Leather produced from various wastes of the food industry. For example, the fish skins, which is a byproduct mainly known as waste from fishing and food industry, could have a new purpose by transforming it into an eco-friendly alternative. In the leather tanning and finishing processes, the synthetic materials and chemicals derived from petroleum are replaced with naturally derived polymers, namely biopolymers. Even if it is just a partial replacement, the effect on carbon footprint could be consistent. For example, the BioNAD project used a new category of naturalized dyes as innovative colorants for the leather industry. Naturalized dyes are deriving from the association between a dye and the sugar lactose obtained from waste milk serum. Regarding the environmentally friendly techniques, the project Showbot offers an interactive tool which could be used among European tanneries and footwear manufacturers. Life Microtan project offers solutions for transformed tannery solid waste materials, collagen and gelatines from non-tan wastes, to valuable co-products. Organic fertilizers, production of biomaterials, gelatines or collagens, and the production of biofuel, useful to be recycled or employed in other industries. Bio-based materials are renewable and provide comparable or even enhanced performance against the traditional materials. Some materials are lighter and others have a unique combination of characteristics, like a combination of rigidity and flexibility and reduced moisture uptake. For example, the Mythos Eco concept of La Sportiva include UGPs made from organic cotton, synthetic silk biopolymers, or vegetable fibers. Soles produced from natural latex, K4F, a mix of coconut husk and natural latex, corn. Insoles made from castor oil. Harder parts, for example in mountaineering shoes, can be made from bio-based polyamides or bio-based thermoplastic polyurethane, TPU. Smart and multifunctional materials. Research studies on intelligent materials are signaled, mainly for the textile and clothing industry. Despite this, the application of the new smart materials into footwear structures is still developing, from both research and technological transfer point of views. New research directions should be taken in the field of smart and multifunctional materials for footwear by integrating consumer-imposed requirements in innovative product concepts. Nanomaterials have the potential to add value to footwear products and to improve the quality of life. Through nanotechnologies, the desired characteristics of the footwear materials can be improved, such as innovative finishing effects of soles and materials through specific surface treatments. Introduction of properties like increased strength, chemical reactivity or conductivity, controlled thermal resistance, high absorbing capacity of sweat and its transformation into heat, etc. Footwear materials that could clean themselves are desirable features, especially for linings materials for footwear having flame retardant properties. Introducing special functions for individuals in healthy needs, such wireless biomonitoring of vital functions at a distance, materials with antibacterial properties. The Project B Nature developed biodegradable leather with minor impact to the environment. This material could be used in footwear manufacturing or other industries, such as automotive, furniture, clothing, aviation. As demonstrated by tests based on the method described in the ISO 20200/2004 standard, after 21 days in composting conditions, this type of leather is completely disintegrated. Recently, various large sportswear industries have announced the market introduction of fully biodegradable high-performance athletic footwear. Biomimetic textile materials are used in footwear manufacturing, especially for their hydrophobic, thermal insulation, and self-cleaning properties. Examples of such materials are: Velcro is used as closing system for footwear textiles with hydrophobic surfaces that imitate the surface of the lotus leaf. Shape memory materials. The Demoshop Princeton Show project developed a high-end female footwear, ergonomic and personalized. The footwear upper materials are based on composites including a shape memory alloy knitted in a textile and placed between internal lining and external leather of the footwear. Materials with thermal or electrical properties. The NanoFoot project developed polymers and composites materials with thermal electrical management properties based on nanoparticles nanofillers. These polymers are applicable in footbeds, insoles and soles, having thermal conductivity and antistatic properties for various applications. Waterproof and or breathable materials. The waterproof technology combines the waterproof and breathable membranes. Characteristics and quality of these materials enable the foot to stay dry even under extreme climatic conditions. Lesson 2.2. Engaging digital engineering tools for innovative footwear. This section is structured into the following topics: computer-aided design, CAD virtual and rapid prototyping, VPRP reverse engineering, augmented reality, AR. Computer-aided design, CAD, represents the use of computer systems, or workstations, in the process of creation, modification, analysis, or optimization of a design. Some of the CAD software for footwear available on the market are iCAD 3D Plus developed by Nescop and Red21, Spain, MindCAD developed by Mind, Portugal, Naxos developed by Tessia, Italy, Shoemaster developed by CSM 3D, United Kingdom, Romans CAD developed by Strategies, France. iCAD 3D Plus is a software for footwear design and pattern engineering that integrates into a single program two different environments, Virtual 3D and Technical 2D, which work in parallel and simultaneously. From sketch to virtual design, the software allowed for the following actions: design, create and modify footwear models, and their patterns, in parallel and simultaneously in 3D or 2D. Flatten lasts for all types of footwear, including boots and ankle boots. Modify the flattening with a single click, create, or import, soles, heels, decorations or accessories. Customize and get images as hyper-realistic as photographs taken from real footwear models. Simulate the appearance of shoes after last slipping, adding realism to your models. The main features of the iCAD 3D Plus software refers to the last in three surfaces, flattened last, shell, pieces, accessories, components, materials and textures, combinations and configurator, rendering, technical sheets. In order to processing the last with iCAD 3D Plus software, the following actions should be considered: select the last from database, open the last in order to edit the three surfaces, edit the cone line, edit the bottom line, move the cone line. Apply front and back symmetry lines, define the mesh. Step 1, average line of the last, Define the mesh. Step 2. Flatten the last, save the flattened last, save the last in 3 surface. In order to 3D modeling of uppers with iCAD 3D Plus software, the following actions should be considered. Open the last for creating a new model, draw design lines, mirror model lines, create pieces, edit pieces, margins to pieces, padding. Stitches, create shoelaces, apply colors and textures to pieces. In order to 3D modeling of bottoms with iCAD 3D Plus software, the following actions should be considered. Create sole, apply colors and textures to bottom components. For rendering the model, the software allows to define the environment type, the rendering process, save the model picture. The main features of MindCAD software are an intuitive interface that allows the user to work in a productive way, the interaction in real time with the design, a realistic representation of the product. The integration between 3D and 2D applications, the instruments, the way of using it, the interface, are similar from 3D to 2D. The software producers stay in touch with all their partners and clients from industry and schools, so the software benefits from their feedback, a precise method of patterns grading and a full range of size numbers that can be obtained. Rapid prototyping involves virtual prototyping and provides physical models as an end product. With advancing CAD/CAM systems, 2 types of prototyping could be used in product design for modeling and simulating products' performances. A. Virtual prototyping that is using analytical models. B. Physical prototyping that allows for computer-assisted manufacturing of physical models. The rapid prototyping technology remarkably reduces the lead time to produce physical prototypes necessary for design verification by generating prototypes directly from CAD data. An example of using rapid prototyping for 3D printing of footwear components, heels, and lasts is given in the above figure. The printer used is Prusa i3 MK2. This 3D printer is versatile, being capable of printing with various available materials on the market, including acrylonitrile butadiene styrene, ABS, polylactic acid, PLA, high-impact polystyrene, HIPS, polypropylene, flex, and nylon. The reverse engineering method is used to design new improved products starting from the existing ones. By eliminating the identified disadvantages, a complete or partial redesign of the existing product leads to a new product. The new footwear model will meet the design criteria based on both new technologies and information collected by market research. In the footwear industry, by reverse engineering can be achieved a product that is especially suited to a consumer or class of consumers, starting from the functional or structural requirements of the feet. The initial information can be obtained by scanning the foot and by biomechanical analysis. Anthropometric maps, longitudinal and transversal dimensions, perimeters, angles, heights, as well as static and dynamic pressure values are registered. Augmented reality, AR, is defined as a real-time direct or indirect view of a physical real-world environment that has been enhanced or augmented by adding virtual computer-generated information to it. Augmented reality is a technique that can be used for visualizing footwear usage. Ideally, it allows users virtually to try out different shoes and accessories, with only a camera and suitable application which encompasses different apparel choices. References for Lesson 2.1. References for Lesson 2.2.